Hi, I'm Ben, and today we're working on rational functions. Our objectives today are to look at rational functions, consider vertical asymptotes, and then horizontal asymptotes. Then we're going to look at identifying asymptotes. Then rational equations. So let's look first at a rational function. Generally, we say a function f represented by f of x is equal to p of x over q of x, where p of x and q of x are polynomials and q of x is not equal to 0, is a rational function. So f of x is a rational function if it can be written as p of x over q of x, where p of x and q of x are polynomials and the denominator is not 0. So let's determine if the following functions are rational, and then we'll state their domains. So a, f of x is equal to x cubed minus 5x plus 1 over 4x minus 5. Well, this is certainly a polynomial, and this is a polynomial. This does not equal 0 necessarily, so f of x is in fact a rational function. What's its domain? Well, when we're finding domain, the main thing to remember is that you can't divide by 0. So how would we end up accidentally dividing by 0? That would happen when 4x minus 5 is equal to 0. When does that happen? That happens when 4x is equal to 5, or when x is equal to 5/4. So, as long as x is not equal to 5/4, this function's just fine. So its domain is the set of all x such that x does not equal 5/4. How about b? This is the absolute value of x minus 1 over x plus 1. Well, this is not a polynomial, so this can't be a rational function. We could still talk about its domain. You still can't divide by 0, so x will work as long as x is not negative 1, but it's not a rational function. So let's look at asymptotes. Asymptotes, especially vertical and horizontal asymptotes, tell us a lot about functions. The vertical asymptote is the line x equal k would be a vertical asymptote of the graph if f of x goes to infinity or f of x goes to negative infinity as x approaches k from either the left or the right. That's the vertical asymptote. The horizontal asymptote has a similar definition. The line y equals b is a horizontal asymptote of the graph of f if f of x approaches b as x approaches either infinity or negative infinity. So as x gets very, very positive or x gets very, very negative, f of x approaches b. So how can we find vertical and horizontal asymptotes? Well, let f be a rational function given by f of x is equal to p of x over q of x. And the key here, written in lowest terms. Finding the vertical asymptote now, we follow the following logic. To find the vertical asymptote, set the denominator, q of x, equal to 0 and solve. If k is a 0 of q of x, then x equals k is a vertical asymptote. Now be careful. If k is a 0 of both q of x and p of x, then f of x is not written in lowest terms, and x minus k is a common factor. The horizontal asymptote is a little bit different. If the degree of the numerator is less than the degree of the denominator, then y equals 0, the x-axis, is a horizontal asymptote. That's part A of the horizontal asymptote. If you have a higher exponent in the denominator than in the numerator, then the horizontal asymptote will be right on the x-axis. But part B is a little bit different. If the degree of the numerator equals the degree of the denominator, then y equals a over b is the horizontal asymptote, where a is the leading coefficient of the numerator and b is the leading coefficient of the denominator. And then C. If the degree of the numerator is greater than the degree of the denominator, then there are no horizontal asymptotes. So let's take a look at a couple of equations. For each rational function here, determine any horizontal or vertical asymptotes. Well, let's take a look at them first. Take your graphing calculator, go to y equals, and then in parentheses 6x minus 1, close parentheses, divided by the group 3x plus 3, close parentheses, and graph. All right, well, it should be pretty straightforward that right there where that vertical line is, that's going to be our vertical asymptote. And then you can tell if you look out to the left and to the right, there seems to be a horizontal asymptote as well. So what are they going to be for this first one? The vertical asymptote happens where 3x plus 3 is equal to 0. So 3x plus 3 equals 0. 3x is equal to negative 3, or x is equal to negative 1. So we should have a vertical asymptote where x is equal to negative 1. As far as our horizontal asymptotes go, we have degree 1 polynomials on the top and the bottom. So the horizontal asymptote will be 6 over 3, or 2. So we should have a horizontal asymptote at y equals 2 and a vertical asymptote at x equals negative 1. So if we look at our graph that we had earlier, you can see that there is in fact a vertical asymptote there at x equals negative 1, and if you count up 2, you should be able to draw a straight line through y equals 2, and that would be your horizontal asymptote. Let's look at b. Again, we go to our graphing calculator, and then we type in x squared minus 1 divided by the group x plus 1. When we graph that, we get this straight line here. So this is a linear function. What the problem is that x squared minus 1 can be reduced. So x squared plus 1 times x squared, or x plus 1 times x minus 1, that's x squared minus 1. So we can take x squared minus 1 over x plus 1 and write it like this. Now x plus 1 cancels with x plus 1, and we can rewrite h of x is equal to x minus 1. Now this is only true when we're in our domain. Remember, the original domain for h of x is set of all x such that x is not equal to negative 1. If x is equal to negative 1, then you get 0 in the denominator here. So h of x is equal to x minus 1, so long as x not equal to negative 1. So that's just basically a linear equation with a hole in it at x equals negative 1. There are no vertical asymptotes, no horizontal asymptotes. So we're pretty much done with that. Let's take another look at another problem. Find all real solutions to the following equation. Check your results. 35 over x squared is equal to 4 over x plus 15. Well, to solve this, let's go ahead and multiply both the left and the right-hand side by x squared. That's going to give us just 35 here on the left, equal to 4x plus 15x squared. So now let's rewrite this. 0 is equal to 15x squared plus 4x minus 35. Well, it turns out that this factors very nicely for us. This factors into 0 is equal to 3x plus 5 times 5x minus 7. If you don't see that immediately, feel free to use the quadratic equation. So what are our roots here? Our roots occur when 3x plus 5 is equal to 0, or when 3x is equal to negative 5, or when x is equal to negative 5/3. And then also when 5x minus 7 is equal to 0, or when 5x is equal to 7, or where x is equal to 7/5. So these are the solutions. So now we need to go back and check. Go ahead and plug in 7/5 in for x, and then negative 5/3 in for x, and it'll work out. Let's try one more. This is one for you to do on your own. Find all real solutions to the following equation and check your results. 1 over x plus 2 plus 1 over x is equal to 1. Go ahead and hit pause and then come back and we'll do it together. So find all the real solutions to the following equation and check your results. 1 over x plus 2 plus 1 over x is equal to 1. Well, let's go ahead and rewrite this. Let's say it's x times x plus 2 times 1 all over x plus 2 plus x times x plus 2 times 1 all over x, and that's equal to 1 times x plus 2. All right, well now we can cross some things off. This x plus 2 cancels with that x plus 2, this x cancels with that x, and so we're left with x plus 2 times 1, so it's still x plus 2, is equal to x times x plus 2. So from here, it's pretty straightforward. This is 2x plus 2 is equal to x squared plus 2x. Subtract 2x from both sides, subtract the 2 to put it over there, and we end up with 0 is equal to x squared minus 2. Well, x squared minus 2 equals 0. We can just say that x squared is equal to 2, so x is equal to plus or minus the square root of 2. So to check your result, you take positive square root of 2 and negative square root of 2 and plug it in for x. So 1 over square root of 2 plus 2 plus 1 over the square root of 2 is equal to 1. Go ahead and plug it in and check it out, and you'll see that it's right. Let's talk about an application problem. The grade x of a hill is a measure of its steepness. For example, if a road rises 10 feet for every 100 feet of horizontal distance, then it has an uphill grade of x is equal to 10 over 100, or 10%. So 100 feet horizontally, 10 feet up, this is a 10% grade. So let's use a problem using grades. Try a problem there. Grades are typically kept quite small, usually less than 10%. The braking distance, d, for a car traveling at 50 miles per hour on a wet uphill grade is given by d of x is equal to 2,500 over 30 times the group 0.3 plus x. So evaluate d of 0.05 and interpret the results. Well, what we need to do here is plug in 0.05 for x. So we have d is equal to 2,500 over 30 times 0.3 plus 0.05, or d is equal to 2,500 over 30 times 0.35. When you do that, you come up with the answer d is equal to 238. So it takes 238 feet to stop going uphill on wet gravel at 50 miles per hour with a 10% grade. How about part B of this problem? Describe what happens to the braking distance as the hill becomes steeper. Does this agree with your driving experience? Well, remember, d is equal to 2,500 over 30 times 0.3 plus x. As x gets larger, so as the hill becomes steeper, the denominator increases. As the denominator increases, d drops. So the steeper the hill, the shorter time it takes to brake. So that makes sense. If the hill is steeper going up the climb, it takes less distance to stop. How about part C? Estimate the grade associated with a braking distance of 220 feet. Here what we're saying, if the distance is 220 feet, that's going to be equal to 220 equals 2,500 over 30 times 0.3 plus x. So from here, what we need to do is multiply both sides by 30 times 0.3 plus x. That's going to be 220 times 30 times 0.3 plus x equals 2,500. And then we're going to go ahead and do the multiplication. When we go ahead and distribute everything through, we get 6,600. X is equal to 520. Just go ahead and do your multiplication and then bring all the constant terms to the right. So now divide both sides by 6,600, and that isolates x. X is equal to 520 over 6,600, and that's about 0.079. So the grade would have to be about 7.9%. Remember, to get from decimals to percentages, move the decimal place over 2, and you get 7.9%. So let's try another application problem. The weight y of a fiddler crab is directly proportional to the 1.25 power of the weight x of its claws. A crab with a body weight of 1.9 grams has claws weighing 1.1 grams. Estimate the weight of a fiddler crab with claws weighing 0.75 grams. All right, to do this, we need to say that weight y is proportionally related to the weight of its claws to the 1.25 power by some constant k. So we need to solve for k. The way we do that is we take the information given. The body weight of one crab, which is 1.9, is equal to k times the weight of its claws, 1.1, to the 1.25 power. So solve for k. You take 1.9 over 1.1 to the 1.25 power, and you end up with k is equal to 1.6866. So if this is k, we can plug it in for k here, and we have the claw weight for the crab we're interested in, 0.75. So we're going to say that y is equal to 1.6866 times x, which we know is 0.75, to the 1.25 power here. And if we go ahead and just plug that into our calculator, we end up with y is approximately equal to 1.177. So the crab weighs approximately 1.18 grams. So today we worked with rational functions. There are a lot of problems like these in your book, so give those a try before you come back next time and we take on a new problem.